Welcome everyone. Today, I'm excited to present on the topic determination of molarity of KMnO₄ solution. We'll be using standard oxalic acid for this experiment. This presentation, prepared by KMnO₄, will guide you through the process of calculating the molarity of potassium permanganate solution. We'll cover the basic concepts, the procedure, and some important calculations. Let's get started and explore this interesting titration method together. Today, we're focusing on how to determine the molarity of a potassium permanganate, or KMnO₄, solution using a standard solution of oxalic acid. This method is quite common in analytical chemistry because it allows us to find the concentration of an unknown solution accurately. The key idea here is that oxalic acid acts as a standard, meaning its concentration is known precisely. We use it to titrate the KMnO₄ solution, which is our unknown. By carefully measuring how much oxalic acid is needed to react completely with the KMnO₄, we can calculate the molarity of the permanganate solution. This process is important because KMnO₄ is often used as an oxidizing agent in various chemical analyses, so knowing its exact molarity is essential for accurate results. And of course, this method highlights the importance of titration techniques in quantitative analysis, which is a fundamental aspect of chemistry. Prepared by KMnO₄, this technique will help you understand how to determine unknown concentrations effectively. Today, I will talk about how we determine the molarity of a potassium permanganate, or KMnO₄, solution by titrating it against a standard solution of oxalic acid, which has a concentration of 0.1 m. The main goal here is to accurately find out the concentration of our KMnO₄ solution, and we do this through a titration process. This method is common in analytical chemistry because it allows us to determine unknown concentrations precisely. By understanding this process, we can ensure our solutions are correctly prepared for various applications. The key concept is that oxalic acid acts as a reducing agent, while KMnO₄ is a strong oxidizing agent, and by carefully controlling the titration, we can calculate the molarity of the KMnO₄ based on how much oxalic acid it reacts with. This connection between the titrant and analyte is fundamental in analytical techniques, and it ties into the overall theme of accurately quantifying chemical solutions. Let's talk about the key reagents involved here. First, KMnO₄, or potassium permanganate, is a strong oxidizing agent. That means it has a powerful ability to accept electrons and cause oxidation in other substances. On the other hand, oxalic acid acts as a reducing agent, meaning it donates electrons and gets oxidized itself. Now, for this reaction to proceed effectively, it requires an acidic medium. The acidity helps facilitate the transfer of electrons, making the redox process smoother. Additionally, heating the mixture to around 60 to 70 degrees Celsius is necessary to speed up the reaction and ensure it goes to completion. One interesting point is that KMnO₄ is self-indicating. This means it has a built-in indicator property. As the reaction reaches its endpoint, the color changes to pink, signaling that the titration is complete. So, in summary, understanding the roles of KMnO₄ and oxalic acid, along with the conditions like acidity and temperature, is crucial for accurately performing this titration. It ties back to our overall theme of mastering redox reactions and their practical applications in analytical chemistry. Let's take a closer look at this chemical reaction. On the left side, we have potassium permanganate, or KMnO₄, reacting with oxalic acid, H₂C₂O₄, and sulfuric acid, H₂SO4. The equation shows that 2 moles of KMnO₄ react with 5 moles of oxalic acid and 3 moles of sulfuric acid. Notice how these reactants transform into products: potassium sulfate, MnSO4, carbon dioxide, and water. The key here is the mole ratio between KMnO₄ and oxalic acid, which is 2 to 5. This ratio is crucial because it helps us determine the exact proportions needed for the reaction to go to completion without excess reactants. It also illustrates the stoichiometry that underpins many titrations and analytical techniques. Overall, understanding this reaction and the mole ratio is fundamental in grasping how redox reactions are balanced, especially in practical applications like titrations or chemical analysis. Let's start by looking at the apparatus we'll be using for this titration. We have a burette, pipette, conical flask, beakers, and a funnel. Each piece plays a crucial role in ensuring our titration is accurate and efficient. The burette is used to dispense the titrant, in this case, potassium permanganate solution, very precisely. The pipette allows us to measure a specific volume of oxalic acid solution, which is our analyte. The conical flask is where the reaction happens, and the funnel helps us fill the burette without spilling. Moving on to the chemicals, we have 0.1 molar oxalic acid, which is our solution of interest. The KMnO₄ solution is our titrant, and it's essential that it's prepared accurately. Lastly, dilute sulfuric acid is added to the oxalic acid to provide the right acidic environment for the reaction to proceed efficiently. All these apparatus and chemicals are fundamental to carrying out a precise titration, allowing us to determine the concentration of oxalic acid accurately. All right, let's go through the procedure step by step. First, I fill the burette with a standard solution of potassium permanganate, KMnO₄. This will serve as our titrant. Next, I pipette exactly 10 milliliters of oxalic acid into the conical flask. It's important to measure this carefully to ensure accuracy. Then, I add 10 milliliters of dilute sulfuric acid, H₂SO4, to the flask. This acid helps to maintain the right acidic environment for the reaction. After that, I gently heat the mixture to a temperature between 60 and 70 degrees Celsius. Heating speeds up the reaction and ensures consistent results. Once heated, I titrate by slowly adding the KMnO₄ from the burette until I see a light but permanent pink color. This indicates the endpoint, where all the oxalic acid has reacted. Finally, I repeat the process to obtain concordant values, those that are very close to each other, to ensure precision and reliability in our results. This procedure is fundamental in understanding how titration can be used to analyze concentrations accurately. Let's take a look at the trial volumes used. In Trial 1, we used 11.8 milliliters. For Trial 2, it was slightly less at 11.6 milliliters. Then, in Trial 3, we measured 11.7 milliliters. As you can see, these values are very close to each other, which is a good sign of consistency. The concordant volume, or the average of these three trials, comes out to exactly 11.7 milliliters. This consistency is important because it indicates that our method is reliable and reproducible. Small variations like these are typical, but having them so close helps us confirm that our procedure is solid. Overall, these results support the idea that our measurement process is precise, which is crucial for the accuracy of the overall experiment. Now let's look at the final stage, which is the appearance of a faint, permanent light pink color that lasts for about 30 seconds. This is a crucial indicator because it signifies a specific point in the process. The light pink hue is subtle but persistent, meaning it doesn't fade immediately. It remains steady for half a minute. This visual cue helps us determine that a particular reaction or condition has been reached. Recognizing this pink coloration is important because it confirms that the process has successfully progressed to this stage, and it allows us to make informed decisions about the next steps. Remember, this faint pink color is a key endpoint marker, ensuring we're on the right track in our overall procedure. All right, let's look at the given values. We have V2, which is 10 milliliters, and M2, the concentration of 0.1 molar. The initial volume, V1, is 11.7 milliliters. Our goal here is to find the initial concentration, M1. To do that, we'll use the dilution equation, which tells us that M1 times V1 equals M2 times V2, so, plugging in the numbers, M1 equals 0.1 times 10 times 2, divided by 5 times 11.7. When we carry out the calculation, M1 comes out to approximately 0.03418 molar. Rounding it, we get about 0.0344 molar. This calculation is a great example of how we can determine the original concentration of a solution based on dilution data. It highlights the importance of understanding the relationship between concentration and volume, which is fundamental in many chemistry applications. By mastering these calculations, we can accurately prepare solutions and interpret experimental results, keeping our overall theme of precise laboratory work in mind. Now, let's look at the key result from our titration experiment. The molarity of the KMnO₄ solution we used is 0.0344 m. This value is crucial because it tells us the concentration of our potassium permanganate solution in moles per liter. Having this molarity allows us to accurately determine the amount of reactants involved and ensures the precision of our calculations. It also helps us compare solutions or replicate the experiment in the future with confidence. Overall, establishing this molarity is a fundamental step in analyzing our experiment's outcome and connecting it to the broader concepts of solution chemistry and stoichiometry. All right, let's go over the key steps for the titration process. First, we need to heat the oxalic acid gently. This helps to ensure it dissolves properly and reacts completely during titration. Next, it's important to use only dilute sulfuric acid, H₂SO4, to maintain safety and accuracy in our reactions. Remember, adding concentrated acids can be dangerous and may skew our results. After that, we need to carefully remove any impurities of potassium permanganate, KMnO₄. These impurities can interfere with the titration, so thorough removal is essential for precise measurements. When performing the titration itself, we continue adding the titrant until we see a permanent pink color. This pink endpoint indicates that we've reached the point of neutralization, so watch for that stable color change. Finally, always note the burette readings very carefully. Accurate recording of these values is crucial for calculating the exact amount of oxalic acid present. Throughout the process, keep these precautions in mind to ensure our results are reliable and safe. Let's go through some key questions about this titration process. First, why is KMnO₄ a self-indicator? Well, because it has a distinct purple color that changes once the reaction is complete, signaling the endpoint clearly to us. Next, why do we heat oxalic acid? Heating speeds up the reaction, making it more efficient and ensuring the titration proceeds smoothly. As for why we use sulfuric acid, H₂SO4, it provides the necessary acidic environment, which is essential for the potassium permanganate to react properly with oxalic acid. Moving on to the endpoint color, it typically shifts from a deep purple to a faint pink or colorless, indicating that all the oxalic acid has reacted. Finally, this is a redox titration, because we're involving oxidation and reduction reactions, specifically the reduction of MnO ions and the oxidation of oxalic acid. All these points are interconnected and crucial for understanding how this titration works effectively in our analysis.